Okay, so this is alkenes, structure and properties. Alkanes and alkenes are both going to be nonpolar, insoluble in water, low boiling points, and with 2 to 4 carbons, they're going to be gases, and greater than 5 carbons, they're going to be volatile and they will vaporize. So they are insoluble in water, meaning they don't have any hydrogen bonding, right? And because of that, if they're nonpolar as well, that means they don't have a dipole-dipole, meaning they only have LDL, London dispersion, which causes that low boiling point, right? Because we remember that LDL is the weakest, then it goes dipole-dipole, and then it goes hydrogen bonding. So the more intermolecular forces you have, the higher your boiling points, and the higher your boiling points, freezing points, everything will be. However, because alkanes and alkenes are nonpolar and are insoluble in water, meaning they are missing that dipole-dipole moment in the hydrogen bonding, they are only going to have London dispersion, which is that induced force, right? Let me make a quick kind of. So right here, this is an instantaneous dipole, while this is an induced dipole. So an instantaneous dipole is going to cause that induced dipole. And the reason why LDL's London dispersion forces are have low boiling points and are so much more weaker is because, again, they are induced. They're not going to have that dipole moment forever, which is what causes it to be a weaker type of intermolecular force. Moving on, over here we look at ethylene, and again, ene is going to be what describes that double bond, right, is what we're going to represent, because alkanes had single carbon bonds. Alkenes are going to have those double bonds. So this has a trigonal-planar geometry at each carbon, and we know that because there's a single bond, single, double, which makes 3 total bonds, making it sp2 hybridized at each carbon, and that creates a 120-degree bond angle at each one. So you need 3 equivalent orbitals on each carbon, which are oriented in the 3 directions of the trigonal planar. That is what we're pretty much just saying, that each of the sp2 hybridized have to point in the directions of the trigonal planar. And then down here we have I can't remember what this is called, but this is pretty much the valence electrons in a carbon, right? So carbon has 4 valence electrons. We see 1, 2, 3, 4. This is specifically for sp2 hybridization. It hybridizes the 2s orbitals and the 2p orbitals, right? So for sp2 hybridization, it's 2s and 2p orbitals, meaning we're taking this and we're hybridizing it with these 2. That gives us 3 sp2 orbitals and 1 p orbital, whose geometry we'll look at right down there. So sp2 hybridization within the carbon then allows 2 sp2 carbons to bond. So important to note here is that this is the hybridization of just 1 carbon, right? I wish that would have stayed, but that's the hybridization of just 1 carbon. Then using this hybridization, we can create a bond with another one, right, within 2 carbons. So this is, right down here, this is what it's going to look like, right? So orbitals on each sp2 hybridized carbon. That was like what I made up there, except mine looked bad. Is like that, and then like that, right? So that's going to be a p orbital, which is perpendicular to the sp2 hybridized plane. And then we're going to have sp2 and sp2. And again, these are at the corners of the trigonal planar. It has sp2 right there and sp2 right there. Then we have a p orbital that sticks out, right? And that is what's going to cause our bond length to be shorter as well, is because that p orbital, actually we'll get to that. So down here we have an orbital bonds to the hydrogen s orbital bonds the sp2 orbitals to make a carbon-hydrogen bond. So right here is sp2, sp2, sp2. Right here is the s orbitals of the hydrogen, which then bonds right here, creating sigma bonds. So keep in mind that this is hydrogen, hydrogen, and then this is the carbon, which is what's reaching out and bonding, using its sp2 and H to make that sigma bond. Then within the carbon and the carbon, there's also a sigma bond being formed to connect the two carbons. So then overlap on the internuclear axis to form the carbon double bond. Non-hybridized p orbitals buries the sp2 to form the pi bond, which is what we see down here. This is one pi bond forming, and this is the this is the p. This is the p orbital that was not hybridized. So as you can see that it's burying the sp2 within itself. And then electron density is going to be found above and below the internuclear axis right here. And that causes that one pi bond to form. Then we look over here and we see that, we look back and we see that the carbon-carbon sigma bond is nestled inside of the carbon-carbon pi bond. The pi bond is perpendicular to the sigma bond. And again, pi bond, sigma bond, right? So the carbon double bond is shorter than the carbon single bond because the pi bond pulls the two atoms closer together. All 6 atoms of the double bond system are in the same plane, so the double bonds are flat, right? So there can be no carbon double rotation, or the two adjacent p orbitals will become orthogonal. Orthogonal means there's a 90-degree angle to each other and can no longer overlap. This pretty much means that no carbon double bond rotation, or the two adjacent p orbitals will become orthogonal, would break the double bond. So no carbon double bond rotation, or it would break the double bond. Okay, so the lack of rotation around the carbon double bond leads to fixed stereochemistry around the carbon double bond, and that leads to there being an ability to be cis and trans, but that's only in alkenes. Now, again, just think of doubles, right? Double bonds. That's what alkenes are. That's the difference between them. So because we have cis and trans, we have to consider how intermolecular forces are impacted. If you take a look at these two, the only difference between them are that one is cis and one is trans. Let's take a quick look at cis isomers though. That's going to be non-hydrogen groups that are on, non-hydrogen groups are on the same side of the carbon double bond, right? And so the chlorine and the chlorine right here are on the same side. On the right side over here, we have trans isomers, and that's when non-hydrogen groups are on the opposite sides of the carbon double bond. You can see chlorine and chlorine are on opposite sides. So that gives us our trans 1,2-dichloroethane, and this gives us our cis 1,2-dichloroethane, ethene, whatever. So right there, like, they look the same, but they have different geometries. So we have to look for which one has these stronger intermolecular forces. There's no hydrogen bonding, right, because that's between HO and F. And obviously we don't see a hydrogen bonding with an O or an N or an F. However, we can see there's a dipole-dipole, right? And dipole-dipoles are polar. How do you know if something's polar? So right here, carbon is less electronegative than chlorine. So we draw our arrow like this. And always keep in mind that this looks like a plus sign, so carbon is going to be S+. These are two arrows right here. So imagine physics, right? There's that rule of tip to tail. In here, when you take the tip of this and you attach it to the tail of this, they don't cancel out, right? You get a dipole-dipole moment that looks like that. Or maybe it's at a different angle, but right now I just do it in like that. But pretty much these forces, they don't cancel, right? That electronegativity does not cancel, which makes the molecule polar. So we know that the cis molecule is going to have a dipole-dipole. Right here, though, the chlorines are on opposite sides, right? So again, we use tip to tail. We take the tip of this and we attach it to the tail of that. Or like we extend it out to the tail of that. And because of that, they cancel. And it makes sense, right? They are on opposite sides. Let's say that this is a positive and this is a negative. Positive, negative. They're going to cancel, which means that there's no dipole-dipole. There's also no hydrogen bonding because, again, we need the hydrogen bonding to an O or an N or an F. But the hydrogen is only bonding to a carbon. So there's only LDL in here. And what did we say on the previous page? Bonding strength goes lowest LDL to dipole to H bonding. Right? We don't have hydrogen bonding, but we have dipole in here, which means that the cis has a stronger intermolecular force than the trans. And stronger intermolecular force is going to mean higher boiling point, higher melting point. It's good to remember that as just stronger intermolecular force means stronger boiling, stronger melting. It's going to be harder to break those down. So this is retinol. We see through photochemical interactions between opsin, which is a protein receptor, and cis-trans retinol. HV light goes in to interact, and then through isomerization, we get a trans retinol from the cis retinol. So the cis retinol is going to absorb light and undergo cis-trans isomerization into the trans retinol. This changes the shape of the retinol molecule. Isomerization itself is a change in shape to accommodate and interact with the surrounding. Okay, so it is activated through outside energy source for isomerization to occur. In this case, it was light. Light went in, isomerization occurred to, again, like accommodate and interact with the surroundings, and in order to do that, it turned into the trans retinol. So as a quick breakdown, alkene, again, ene is going to be the one that tells us that there is a carbon double bond, right? An alkene is one carbon double bond, right? And the suffix is ene. Diene contains two carbon double bonds. Di is two. Ene is going to stand for our carbon double bond, right? So polyene is going to be a compound containing more than two carbon double bonds. Example, triene, tetraene, pentene. The prefix is always going to be ene. So multiple bonds, right, can be either accumulated, which is back-to-back carbon double bonds, conjugated, which is altering carbon single bond, carbon double bond, carbon double bond, carbon single, carbon double, carbon single. And then isolated is when neither of the above are occurring. So there's a double bond, then there's a single, then there's a single, then there's a double, right? So more than one carbon single between carbon doubles.